my oscillating formula for epsilon sub naught, I have C, whatever my maximum is, cosine omega t plus phi is equal to Q. Because I want to know what the relationship with charge is, I am going to, well, do the change with respect to time. So I've run out of room there. Well, Jesse, write that down, and then I'm going to go to the next screen. So I have Q is equal to whatever my capacitance is times epsilon max cosine omega t plus phi. So the change in Q over the change in time is going to be C epsilon sub naught cosine omega t plus phi. Now the reason I didn't stick the C and the epsilon sub naught, oh, I suddenly changed notation there, epsilon sub m. The reason why I did not put those on that side of the delta is the fact that they're constants, they're not changing at all. So now it's a question of what is this is just the graph of the slope of my cosine curve, which we did 2 weeks ago. Yes?
What is that letter symbol after the triangle below the T?
That?
Yeah.
That's a T. Apparently I erased it because I was meant to rewrite it. So the slope of a cosine curve?
Negative sine.
So this becomes C epsilon sub m. The omega is going to pop out front, omega negative sine omega t plus phi. So that will be my current. My maximum current is going to be equal to omega c epsilon sub max. And put it in a slightly different form, I have my maximum voltage, or maximum EMF, is going to be 1 over omega c times I. All I did was just take that, bring it over to the other side. All right, there are a couple things coming out of this. Number one, I have delta, that's my voltage, is equal current times, I know Ohm's law, V equals IR, or delta V equals IR, but this isn't really a resistance. But since that's in volts and that's in ohms, this has to since that's in volts and that's in amperes, this has to have volts of ohms, or sorry, wow, take 3. Since this is in volts, this is in amperes, this has to have units of ohms. That was said correctly. But it's not a resistance, it has, but it seems to be kind of like a resistance. It has the right units for resistance. It, I guess, has some function like that. So what the powers that be decided to do is to call it something else. It's not resistance. It'll be represented by the letter X, capital X, lowercase c. And this is the capacitive reactance.
Is the entirety of it being 1 over,
Omega.
omega c, that whole thing is xc?
Yes.
Okay.
So one thing we have here is we've now defined capacitive reactance. So capacitive reactance is equal to 1 over omega c, where omega is the angular frequency, and c is the capacitance. Given that, we have response of x equals the maximum current, x and c. So if I were to plot of the EMF, and I've been drawing that capitalized, that really should be a lowercase epsilon. Or that is big epsilon. This has, that's time, this has a period of 2 pi over omega. And so for the capacitor, my current, though, is a negative sine graph. See, sine starts here, negative sign goes down, so it's going to bottom out there, 0. And that's my current. Where that value would be negative. And again, the green and the black are on 2 different vertical scales. So if you draw the green one bigger than the black line, that's fine. It just, I typically, whatever the first one I do, I draw bigger than the second one.
Can you explain why you noted that one part as negative?
Negative I?
Yes, thank you.
Capital I is the magnitude, it's the amplitude. And I is a positive number. It's 1 over omega c. Omega is a positive number, c is a positive number. So, since I is a positive number and I'm below the axis, that's why I made it negative. I could have just as easily, right there, that looks like a negative I, that's a mark. So in terms of time, because remember, time is equal to 0 at my axis, at my vertical axis there. Am I going to bottom out my current first or bottom out my voltage first? Think about the time starts at 0. As you progress to the right, which one troughs first?
Can you repeat the question?
So I have those 2 graphs. Think about time is equal to 0. You're there on the axis. As you move to the right, which one is going to bottom out first? The current or the voltage? Which one peaks first? Oh, you're thinking about it at the very beginning?
Oh, yeah.
Yeah, sorry. Poorly worded.
The current.
Yeah. Ignoring that, I was looking at this right here. So the way this is looking here, as you go from 0 onwards in time, current basically leads. So current bottoms out, and then the voltage bottoms out. Current peaks, the bottom peaks. Current hits 0, the bottom hits 0. Or the voltage hits 0. So, using physics speak, for a capacitor, current leads the voltage by 90 degrees. Now, why 90 degrees? We'll get to that. But that's the ice. For a capacitor, I before E. For a capacitor, the current is ahead of the voltage. What is capital L? I'm pretty sure we did that. Capital L, within the context of this class. Was it 2 weeks ago?
Do you remember how long ago we went from this?
I was thinking it was 2 weeks ago. About this place we were dealing with the solenoid.
L is delta n squared mu sigma over little l. Is it-
Okay, that,
Or, yeah, it also, I also have, sigma equals negative L change in current over change in time. This is the stuff you're asking about.
you have sigma?
It's in the appendix.
Oh, that's one.
Oh, why did I say so?
All right, what does L stand for? I'll just write that over here. So you had epsilon is equal to negative L.
Over
delta.
change in current over change in
That's what we did before. Presumably I broke down what L represented.
Henry,
That's the units.
it's for an inductor.
Yeah, there we go. L is inductance. Which inductors have. Just like a capacitor has capacitance, inductors have inductance. I want to make sure I get my minus sign in the right spot, because if I don't, that'll mess things up badly. So let's do this. So what we're gonna do now, any questions about capacitors? We had resistors, we have capacitors, we're now gonna do inductors. Any questions? So now let's take our AC power supply and stick an inductor into it. So inductance L. Now, for most textbook problems in 152, phi is going to be equal to 0. The reason why I stick it in there is that when we actually do a lab with AC circuits, phi will not be 0. It all matters where you start. Okay, so I know that the voltage gain here is the voltage loss there. I'll have my EMF minus delta VL is equal to 0. Epsilon minus L delta I over delta T. Let's make that slightly better. Epsilon is equal to L delta I over delta T. So epsilon over L is equal to delta I over delta T. What I'm going to do is I'm going to pop in our formula for the alternating potential here. I'm going to plop that in for epsilon. So I have epsilon, so m cosine of omega t plus phi over L is equal to the change in the current over the change in time. So what is current? In other words, what function, when I take the slope of, is going to give me cosine? Before we did the slope of cosine, now we're trying to figure out the slope of what will give us cosine. Go ahead, Luis.
Sine?
Sine, yes. So this becomes epsilon sub m over L sine omega t plus phi. Now, if I go back and I do the reverse, if I do the change, if I look at the slope of this, I should get that. There is an omega that's going to pop out when I do the slope, and so I need to stick omega down here, so that when the omega pops out, it's going to cancel out with that, and we're left with epsilon sub m over L. If you had calculus, this should be a little more intuitive. If you haven't had calculus, flashback to the notes from last Thursday. No, last Tuesday. So this right here is the amplitude of my current. So my maximum current is going to be epsilon, my maximum voltage over omega L. My maximum voltage is equal to I times omega L. So putting it into Ohm's law form, we have my voltage is equal to current times that, which we represent as an X with a lowercase l. Now when I get writing really fast, my L's and C's look very similar. This one's an L. This is, as you might guess, the inductive reactance. So let's write that up over here. We have X sub L is equal to omega L. And that's one M is equal to Y. You know, I should change. Sorry about this.
that works for what we have right here. I'm gonna make it more generalized. This is the voltage, the maximum voltage across the inductor. This is the maximum voltage across the capacitor, and the maximum voltage across the resistor.
I think if we left it as epsilons of m, that's gonna get more confusing as we start adding these components together in some combination. Let's do our plot. My voltage is still a cosine curve. So now I've got a sine curve. Sine starts here, goes up. Now which one leads? You're pointing, but I can't really see what you're pointing.
The voltage.
Yeah. If we start at 0, we move this way, we peak here, then we peak at voltage, but then we peak on the current. So for an inductor, the voltage comes first. And at this point, you're going, how? God, this stuff is just so incredible. It's amazing. But how do we solve the circuit problem? You're on top. We have a way. The next step, to introduce the phasor. Not the Star Trek one. There is a more mathematical way of dealing with all of these using complex numbers. There are problems in which that is so much easier than doing the graphic method, which we're about to do.